Okay, welcome back everyone. So this is going to be the video, well, before my trip to Poland. Um, and don't worry, I'm still going to be making videos in Poland, but there might be a bit of a break between the transition from, where I live right now to Poland. So, yeah, so I won't be uploading videos during that period of time, most likely. And also the time difference is quite gigantic, so my videos might be uploaded at strange times. Um, but yeah, other than that, should be fine. And, well, also, I haven't been uploading for the past 2 weeks or so, because, well, I had a few camps that I had to attend, and I also had to, I also had to have a friend over, so it's kind of hard to record a video while, you have a friend over. But anyway, today's video we're going to just be proving a few properties of dot product and cross product and the derivatives of those products, vector products, um, in order to, actually progress in a future video, probably the next video actually. Might even record it right after this one. I'm not too sure if I have enough time though. So this video isn't that interesting. It's more just a precursor to the next video, like I said. And yeah, there's not many interesting proofs. It's mostly just expanding out the cross product and dot product and things like that. But the last one is um, actually requires a few tricks. But let's just get into it. So let's try the first one. And I strongly recommend that you try all of these because I don't know, they're good for practicing to avoid silly mistakes since they actually require annoying computations. But first, what we want to prove is that the derivative of u dot v. Actually, we'll start with the cross product just to get one of the worst ones over with. The derivative of u cross v is u dot cross v plus u cross v dot. Okay, well, how do we, again? Well, let's expand out u cross v, and let's say u has components, well, u1, u2, u3, and v has components, v1, v2, v3. We're working in 3 dimensions, but these identities can be generalized to multiple dimensions. So yeah, again, let's expand out the cross product by its definition. And well, you can just take the determinant of the following 3x3 matrix. I mean, I don't really memorize the expanded out version of this 3x3 matrix, determinant of a 3x3 matrix, but some people do, so cool if you do, but I don't. U2, so we have the first column, the second column I should say, is with the components of the first vector, and the third column is with the components of the second vector. So how would we calculate this? Well, I forgot what this method is called, but it's like covering up like the horizontal and the column, row and column cover up thing. I forget. Well, we take the determinant of this 2x2 matrix formed by covering these up. So we have u2 v3 minus u3 v2 I hat plus, I should say minus, but we'll just try to swap the two terms in our head. Well, normally it would be u1 v3 minus v1 u3, but we're swapping it, so we have u3 v1 minus u1 v3 j hat plus, well, let's see, u1 v2 minus v1, not k. Why these look like a k to me? u2 k hat. Okay. Well, let's just take the derivative of this. So if we take the derivative of that, what we're gonna get is, well, again, it's important to note that maybe some people get confused, about this, but these are not necessarily constant vectors. Again, maybe I should have specified, but these are vector functions. So they're not necessarily constants, and therefore when you take the time derivative with respect to, again, maybe I should have been a bit more specific, but they take in the parameter t. Just writing these like that. So yeah, we have to use product rule in this case. We can't just, you know, set it equal to 0. So what we have is u2 dot v3 plus u2 v3 dot minus u3 dot v2 minus u3 v2 dot I hat plus u3 dot v1 plus u3 v1 dot minus u1 dot v3 minus u1 v3 dot j hat plus u1 dot v2 minus plus u1 v2 dot minus v1 dot u2 minus v1 u2 dot k hat. Okay, so how do we continue here? Well, let's notice something very important. So I'm going to underline things to pair. I'm going to underline a few things that will pair with one another. So pair these two and pair these two, including the signs. Pair these two and pair these two. Pair these two and pair these two. What do you notice? Well, here, let's consider this example for a second. So when we pair these two, we get u2 dot v3 minus u3 dot v2 I hat. And then if we pair these two, we have plus u2 v3 dot minus u3 v2 dot I hat. Okay. Well, and then the other terms can go so on and so forth. But let's notice what's inside here. And this also applies to the other terms. But if we look at this term here, and then this term, and also this term, and then the first term here, what do you notice? Well, we have that these two are exactly the same, but our u2 and u3, in this case, are exchanged with their respective, time derivatives. And the same thing applies to the rest of these pairs. So you'll have like this I hat plus, the same thing as this, but with u3 and u1 exchanged with their dot version, j hat, etc. And that means that, well, all of these vectors, so these vectors the ones I just described, these are going to exactly be, well, u dot cross v, because v3 and v2, well, and v1 are all kept constant. The only difference is the u vector. It's just taking the time derivative. And then plus, well, all the other components will also show that, well, again, if we look at that, it's the same thing, but with the v3 and v2 exchanged with their respective time derivatives. So you can check, if you just want to expand out the rest of the terms, that will also get u cross v dot. Okay, well, that proves what we wanted to prove here. So let us continue to the next one. Okay. So this next one is much shorter. U dot v equals u dot v plus u dot v dot. So that's what we want to prove again. Now, well, again, let's just expand this out. This is equal to u1 v1 plus u2 v2 plus v3 u3. And if we take the time derivative of this, this is going to be equal to, well, again, using product rule, we have u1 dot v1 plus u1 v1 dot plus u2 dot v2 plus u2 v2 dot plus v3 dot u3 plus v3 u3 dot. Okay, so we should have 6 terms, 2, 4, yep, and it needs to do, oh, whoops. So, well, let's see what we can do here. Okay, well, again, we're gonna do that weird pairing strategy. So, let's pair the following terms together. I'm gonna pair, so I'm gonna pair this term, and this term together. Because as you can see, it's the same idea from the last one. We have the same, the same scalar product, except the u1, u2, and u3 are exchanged with their respective time derivatives. Therefore, these two combine to form, these three, I should say, combine to form u dot dotted with v. And same thing with these three. The v's are exchanged with their respective time derivatives. So we're just going to get plus u dot v dot. Okay, well, that proves this identity. Okay, so let's go to the next one, which is, let's just say it's going to be a bit tedious, to say the least. But let's get it done. So next we want to show that dt of, oh no, sorry, it's not derivative this time, which is somewhat of an improvement since we have to worry about product rule, but you'll see it makes up for that with a bit more annoyance. So what we're going to have is, I'm going to introduce another vector k with also 3 components, k1, k2, k3. And then we're going to show that k, I should say, k dot u1 cross v is equal to k cross u dot v. Okay, well, again, this doesn't seem very intuitive, unlike the other ones maybe, because it's kind of like single variable calculus with the product rule and everything. Well, so how do we approach this? Well, I mean, I don't know why I'm asking that question, because it's the same strategy as the others. Just expand and find equality. So let's try that. If we expand this one out, this one's easier since we already dealt with u cross v. And I erased it, didn't I? Okay, that might make it a bit less efficient. But just to quickly calculate u cross v, this is going to be equal to I hat, j hat, k hat, u1, u2, u3, v1, v2, v3, which is equal to, let's see, so u2, v3 minus u3, v2, I hat plus v3. You see my v's look like u, which is a problem. So u3 v1 minus u1 v3 j hat plus u1 v3 minus v1 u2. Oh, this is wrong. Sorry. v2 k hat. Okay. So that's what we have. Now we just take the dot product of this with k, the vector k. So what does this become? Well, that just becomes, we just replace the I, j, and k with the components of k respectively. And that becomes, should I expand it out or not? I'm not going to expand it out. So we're going to have, well, actually, I'll just, to save time, I'll just try out a fairly large brain strategy, which is to take the dot product here, and then replace these, literally, like I said, but just erase them. K2, K3. Okay, so this is important, right? And now we need to calculate K cross U, dotted with V. So what will that be? So V dot K cross U. Again, dot product is commutative, which is very easy to show. With both the geometric definition and the algebraic definition. So what is this? This is going to be, well, we can kind of just do some replacing. Okay, just making sure. K crossing. Okay, so yeah, let's go. K2 V3 U3 minus K3 U2 V1 plus U3 K3 V1 U1 minus K1 U3 not K V2. I think that's correct. Plus what we have here is going to be K1 U2 minus minus K2 U1. Yes, okay. V3. Okay. Now, what can we do here? Well, let's kind of expand this out in our heads. So when we expand this out, if we take a look at the first two terms, well, when we expand V1 out here, V2 out here, we're going to get, well, I'm going to consider these two terms, and this term and this term. So that's going to be negative K3, so dot dot dot, negative K3 U2 V1 plus V2 K3 U1. Okay, well, our goal is to kind of have this form where we factor out the k's. So what if we factor out the K3 from here? What happens? Well, we get K3 times, let's see, V2 U1 minus U2 V1. Let's look at here. U3 V1. Here U1 V2. Yep, that's exactly what we had. U1 V2 minus U2 V1. Yep. So these terms match. And actually, this will hold for each of our pairs here. We could choose these two pairs, so this pair with this pair, and then also this pair with this pair. Okay, so that actually completes the proof. You can kind of fill in the gaps there by simply writing the full expansion out and then factoring it out manually, but that's as far as I'm going to go. So I would say that's that completes the proof here. And finally, for the last and most interesting proof, perhaps, well, it's going to be rather surprising because it seems like it's the most nasty, but it's going to be that K cross U cross V is equal to, it's also very unintuitive, but it's equal to not cross dot V. I swear, every time I've done this, I've confused the dot with the cross. Every time I've written this. K cross U V. Okay, well, this actually will probably take a shorter period of time than most of the other ones that we've done today. And how? Well, first, let's kind of step back a bit instead of going right into the computations. Look what I did. Let's first define G, the vector G, to be U cross V. So what does this mean? Let's go back to the geometric interpretation of the cross product. Well, this means that G is perpendicular to the plane that U and V lies in. Okay, well, now let's define another vector D, which is equal to K cross G. What does this mean? Well, this means that D is perpendicular to G and K. But this is the important thing, that D is perpendicular to G. That means that it has to lie in the same plane as U and V. Because since G is perpendicular to U and V, and D is perpendicular to G, well, it's kind of like sent back to the plane. There's no other way of thinking about it where it's not set back into the plane. Okay, well, well, let's see. So, and there is possibly a more rigorous way of showing that by perhaps using, that the identity we just proved with dot product, and I'll leave that as an exercise to you. So, but this should be rigorous enough. Anyway, so, and actually D is exactly what we want to solve for, because it's exactly K cross U cross V, and in parentheses. So we need to solve for D in this format. So how do we do that? Well, since it's in the plane with U and V, using some linear algebra, well, that tells us that D has to be a linear combination of U and V. So that tells us that D equals N, K, so just some arbitrary scalars, and an M, V. This, again, I got it confused. Not K, it's U. My bad. Okay, well, now what? Now I'm going to take the dot product with K on both sides. So let's see what that results in. Okay, let's see. So we're going to get D dotted with K is equal to N U dot K plus M U dot V. Okay. And now like I said, we're relating this to the dot product, which is important. But also we're doing this because D dot K is by definition 0, since D is equal to K cross G, and therefore D is perpendicular to both K and G. So 0 equals this linear combination. Okay, well, in order to make sure this holds true for all U, K, and V, all we have to do is set N equal to, well, the trivial case, which is negative, this is a U, right? Negative U, I should say, without loss of generality, or in order to avoid loss of generality. Yeah, we'll let K represent, actually I'll use lambda. So lambda will be some arbitrary constant times, well, actually this is positive. this is positive lambda, n equals positive lambda times, well, let's see, that'll just be u dot v, whilst m equals negative lambda times u dot k. Okay, and notice that if you plug these in, we actually always get 0 for all vectors u, v, and k. Okay, well, let's see. Now, since this works, let's plug it back into our formula for d. And now, actually, what you'll notice is that what's left to show is that lambda is 1. So when we plug it back into d, we just get, well, d equals lambda times, factoring out the lambda, u dot v, oh, sorry. Oh, this, I think oh, this is k, isn't it? Oh, yeah. Again, I confused. So k, I'm pretty sure. So it should be, oh, 1 second. So we're going to have here is, well, n is equal to lambda times k dot v. So, well, in here, I guess I should have 2 parentheses. We're going to have exactly k dot v u minus k dot u and then v. Okay. Again, we just want to show that our lambda is 1. How do we do that? Well, let's just take the case where we have u. Let's just take the case where we have u is j hat. I mean k is j hat, u is j hat, and v is k hat. So in other words, we want to compute j hat cross j hat cross k hat, which is nothing but, well, let's see, just using the right-hand rule, it's easy to see that, well, what is this? This is j cross k hat, j hat cross k hat. With the right-hand rule, it's just easy to see that that's going to be exactly I hat, so we have j hat cross I hat, which is just, again, using the right-hand rule, negative k hat. So we have negative k hat has to equal this, but when obviously we substitute u, k, u, and v, so we have negative k hat equals, and then substituting into our formula here, it's lambda times u cross u dot v. Well, notice that u is j hat and v is k hat, and j hat dot k hat is 0. So 0 minus, so 0 vector technically, because we have our u here. K dot u, well, both of those are j hat, so we have minus, and then since they're normalized with our unit vectors, we just get a 1. So we just get oh, so we actually missed actually swapping the v with the k hat. So when we swap the v with the k hat, we will avoid confusion. And notice that, well, we're just going to get a unit vector dotted with self, which is just 1. Well, let's see. So we're just going to get 1 times k hat, which implies that negative k hat equals negative lambda times k hat. But that just tells us that lambda equals 1. Therefore, proving our identity. So I hope you enjoyed that video, and also possibly completed some of the proofs alongside me, and struggled in all of the nasty computations along with it. So anyways, have a nice day, and goodbye.